Hello friends, I welcome you in lecture number 16 on complex differentiation. Up to this lecture we have discussed about differentiability of complex function and also about analytic functions. Now we are familiar with use of Cauchy-Riemann equations in determining the differentiability as well as analyticity of a complex function. In this lecture we are going to understand harmonic functions. We will see what is the definition of harmonic function and how we can check whether given function is a harmonic in a given domain. Harmonic functions are real valued functions of two variables. For example, suppose I have some function say u of two variables say x and y, where x and y are real variables. So u is a real function of two variables, and suppose we want to check whether u is harmonic in some domain say capital D of the complex plane. Then we should check two conditions. First we have to check whether first and second order partial derivatives of u are continuous in domain D. First and second order partial derivatives of this real function u must be continuous in a domain D. That is the first requirement of harmonic function. Second requirement is this real function u satisfies this equation del square u by del x square plus del square u by del y square equal to 0 in domain D. This equation is special type of equation. It is known as Laplace equation. So a real function u of two variables x and y is said to be harmonic in domain D if these two conditions are satisfied. So you have to determine the first and second order partial derivatives of given function, and then you have to check whether addition of these two second order partial derivatives is 0 everywhere in domain D. Then your function becomes harmonic function. So they can ask the definition of harmonic function, as well as they can ask to verify whether given function is a harmonic or not. So I have written this definition here. You should write systematically in this way. A real valued function u is said to be harmonic in some domain D of the complex plane if these two conditions are satisfied. First condition is first order partial derivatives as well as second order partial derivatives of given function are continuous in domain D. Second requirement is u satisfies this Laplace equation del square u by del x square plus del square u by del y square equal to 0 everywhere in a domain D. We consider one function and we prove that it is harmonic in the complex plane. Here our domain is complex plane, that is xy plane. So it is easy to prove this. First we will find out first and second order partial derivatives of this function. Given function is u equal to e raised to minus y times sin x. So if we differentiate first with respect to x, we consider y as constant. Therefore e raised to minus y is constant. Derivative of sin x is cos x. And if we differentiate with respect to y, we consider x as constant. Therefore sin x is considered as constant, and derivative of e raised to minus y is minus e raised to minus y, and sin x as it is. We require second order partial derivatives also. So now we differentiate this with respect to x again to obtain second order partial derivative. And here e raised to minus y is considered as constant. Derivative of cos x is minus sin x. And we require derivative of this with respect to y to obtain uxy, that is del square u by del x del y. So now we differentiate this with respect to y. So cos x is constant and derivative of e raised to minus y is minus e raised to minus y cos x as it is, and we differentiate this again with respect to y to obtain del square u by del y square. So sin x is constant, derivative of e raised to minus y is minus e raised to minus y, therefore we will have plus sign here, and this is as it is. So now we can see all these first order partial derivatives contain exponential and trigonometric functions sin x and cos x, and we know that exponential as well as sin x and cos x functions are continuous everywhere in the complex plane. So we will directly write the first condition, that clearly this first and second order partial derivatives of u are continuous in the complex plane, and u y y are continuous in the complex plane. So we are not going to prove the continuity, we have to just write down that given functions, given first and second order partial derivatives are continuous in the complex plane. And second requirement is del square u by del x square and del square u by del y square, addition of these two must be equal to 0, that is satisfaction of Laplace equation. And we can observe here, if we add these two, then that is going to be 0 for any point xy in the complex plane. So now we write down that del square u by del x square plus del square u by del y square equal to minus e raised to minus y sin x plus e raised to minus y sin x, and this is equal to 0 for all points xy in the complex plane. This means this function u satisfies Laplace equation, therefore u satisfies Laplace equation in the complex plane or in the plane. Therefore both the conditions are satisfied, and therefore we can say that u is harmonic in the complex plane. So we can see that it is very easy to check whether given function is harmonic in the given domain, and all we have to do is we have to first obtain first and second order partial derivatives, then we have to check two conditions. First condition is continuity of first and second order partial derivatives of u, and second condition is Laplace equation. So if these two conditions are satisfied, then our function is harmonic in the complex plane, and if any of these two conditions is not satisfied, then u is not harmonic. Now we are familiar with analytic function. We know that if we have function f of z, then we can express it in this form, uxy plus I into vxy, by taking z equal to x plus iy in the formula of given complex function. So we have one result which says that if function f of z equal to u plus iv is analytic in some domain D, then these two components u equal to real part of f of z and v equal to imaginary part of f of z are always harmonic in the domain in which function is analytic. Suppose function is analytic in some domain D, then these real and imaginary parts u and v of f of z are always harmonic in domain D. For example, we know that function f of z equal to z square is analytic everywhere in the complex plane, that we have seen in earlier lectures. and if we put z equal to x plus iy and we simplify, then we obtain u equal to x square minus y square and v equal to 2xy. Now we know that this z square is analytic everywhere in the complex plane. Therefore, these two functions u equal to x square minus y square and v equal to 2xy are harmonic in the complex plane. So we will remember this result. We are not going to prove this result. Result is that if function f of z equal to u plus iv is, here I have to write analytic, if f of z equal to u plus iv is analytic in some domain D, then its component functions u and v are always harmonic in that domain D. And this is what we just discussed, that z square is analytic in the complex plane. Therefore, u and v are harmonic in the complex plane. So this is very easy definition. Harmonic function, they can ask you to check whether given function is harmonic in a given domain or not. All you have to remember is two conditions. First condition is first and second order partial derivatives of u are continuous in a domain D. Second condition is u satisfies Laplace equation in a domain D. And if these two conditions are satisfied, then we can say that u is harmonic in a given domain D. So this is all about this session. We will continue with this series in upcoming lectures. Thanks for watching.